In this video, we're going to learn a special factoring strategy that occurs when our A and C values are equal to perfect square values. So the strategy that we're going to be discussing in this video talks about a strategy that can only be used when A and C are perfect squares. So what we're going to do for the 6 situations below is we're going to decide for which of these A and C are perfect squares. So if I look here at this first example, we have an A value that's equal to 4 and a C value that is equal to 25. Both 4 and 25 are perfect squares because they can be perfectly square rooted to produce an integer. And as a result, this strategy would work on this particular expression. Then from here, if we look at the next one, we have an A value that is 9 and a C value that is 1. Again, because both of those can be perfectly square rooted, this will work with the strategy that we're discussing in this video. This next one down here, we have A is equal to 2 and we have C is equal to 9. Well, 9 is in fact a perfect square and can be square rooted easily, but the square root of 2 is a decimal. It's about 1.41 and then it keeps going. Because of that, A is not a perfect square, and as a result, this strategy will not work for that particular expression. Then over here, we have an A value that's equal to 1, which is a perfect square, and a C value that's equal to 10. And if I try to square root 10 perfectly, I end up with a decimal value of about 3 point something. And as a result, because this is not going to produce an integer when it's square rooted, this entire thing cannot use the strategy we're about to discuss. Then here we have an A value equal to 49. Notice that there's no B value in here. Our B value would really be 0. And our C value is equal to 64. Well, both of those can be perfectly square rooted, and as a result, this strategy will work here. And then finally, we have A equals 2, C equals 1. C equals 1 is a perfect square, but A equals 2 is not. So this strategy would not work for that trinomial. So that's the first step, is being able to identify whether or not the strategy we're about to look at truly does work. So on the screen, you should see a trinomial. And if we identify our A, B, and C values here, we find that A is equal to 4, B is equal to 20, and C is equal to 25. So what we're going to focus on here, when we have two perfect squares for A and C, and we have a positive middle term for B. So I'm going to demonstrate this first by looking at the ABC method, because that's going to help us here since our numbers are small enough. So if I start off, I'm going to multiply A times C, 4 times 25, which is 100. And then from here, I'm going to take my B value and I'm going to add to B, which is 20. So I need two numbers that multiply to 100 and add to 20. And as I start thinking about the factors of 100, I notice that 10 plus 10 gives me 20, but 10 times 10 gives me 100. So I'm going to rewrite this piece here as 4x squared plus 10x plus 10x plus 25. And then from here, I'm going to look at it in pairs and find the greatest common factor. So the greatest common factor of the first pair is 2x. The greatest common factor of the second pair is 5. So now as I rewrite that by factoring out those greatest common factors, I get 2x and then 2x plus 5, and then plus 5 times 2x plus 5. And I notice that my parenthesis parts match, which means I can group these front values together. And I end up with 2x plus 5 times 2x plus 5. So what I'm noticing here is that when I have a perfect square for my A value and my C value, what I can really do with that B value there, if it's positive, is split it. I can think, okay, 20 divided by 2 is 10 and 10, And then using the ABC method to help me, I can ultimately get to this point where I end up with 2x plus 5 times 2x plus 5. Now, my second example here, I notice that my A value is 16x squared and my B value is 49. And I know that 16 and 49 are both perfect squares, so I'm going to split 56 evenly because I know I can apply what I just did above. And 56 divided by 2 breaks this up into 28x plus 28x. Then I add on my 49 at the end and my 16x squared at the beginning. So then from here I break it into pairs. I find my greatest common factor, which in this first set is 4x. So that becomes 4x plus 7. And in the second set is 7. And then that becomes 4x plus 7. Now from here, I'm noticing that I have the same parenthesis piece, which then means that I can group together these front two items. And I end up with 4x plus 7 times 4x plus 7. All right. Now looking at example 3, again, I notice that I have 36 as an A value, and that is a perfect square, and 81 as a C value, and that is a perfect square. So I know from here I can split my middle term into 54y plus 54y, then adding the 81 onto the end and the 36y squared onto the beginning. I then from here look at these in pairs and find the greatest common factor. Oop, I forgot a 4 there. There we go. So then from here I notice my greatest common factor here is 6y. Both of those are divisible by 6. So here I have 6y plus 9 as I factor out that 6y in front. And then in this second set, the greatest common factor is 9. So as I factor out that 9, that becomes 6y plus 9 as well. Then because I have matching parenthesis pieces, I can group these in front, and ultimately I end up with 6y plus 9 both times 6y plus 9. Now, as you were working, hopefully you were picking up on another pattern. What you should also notice here is that my A value and my C value are very closely related to the numbers that end up in parentheses down here. So what you should be noticing in each of these is that both parenthesis parts end up being the same, which is a unique result of the fact that we have A and C values that are perfect squares in all three of these examples. And what you should also be noting is that if you square root A and C, so say we square root 4x squared, that becomes 2x, which is the first number in each parenthesis. And if I square root my 25, I get 5, which is the second number in each parenthesis. And then if I look down below, I start to see the same thing. The square root of 16x squared is 4x, first number in the parentheses. Square root of 49 is 7, second number in parentheses. Then if I look at the third example, square root of 36y squared is 6y, first number inside of the parentheses. Square root of 81, second number inside of the parentheses. So if you can see those patterns there, you can use those. Noticing that A and C are both perfect squares allows you to use some shortcuts to help you write these into factored form. So now let's look at what happens when we have an A and a C value that are perfect squares and a middle term that is subtracted. So notice that this is a negative 20 here. So let's start off again with A is equal to 4, B is equal in this case to a negative 20, C is equal to 25. So now I multiply A times C to get 100, and I need to add to B, which is negative 20. So if I start thinking through multiply to 100, add to negative 20, I come up with negative 10 and negative 10. So here I have 4x squared minus 10x minus 10x plus 25. And then if I use my trick from the ABC method, we group them into pairs. This first one will factor out 2x, so I have 2x times 2x minus 5. I then want those parenthesis parts to match, so here I'm going to factor out a negative 5 in order to get 2x minus 5 inside of those parentheses as well. And then I can group these front parts together since the parenthesis parts match. So I have 2x minus 5 and 2x minus 5. So hopefully you're noting that this is pretty much the same process as the previous slide. We have an a value and a c value that are perfect squares, and then the only difference here is this negative middle term. And hopefully you're noticing that you can still square root a and get 2x, and you can still square root c and get 5. The only difference here is that we have a subtracting symbol in the middle of those two numbers this time instead of a plus sign. So now let's look at the next example. Here I'm noticing that a is equal to 25 and c is equal to 1, both of which are perfect squares. So because it has that particular pattern, I can split that middle term into negative 5x and negative 5x, then tack on the 1 and the 25x squared. So then I focus on these in pairs. So this first pair, we can factor out a 5x. So we end up with 5x times 5x minus 1. And then I want those parenthesis parts to match, so I'm going to factor out a negative 1, as that will result in a positive 5x minus 1 in my parentheses. Then from here, I can group the two front parts together since the parenthesis portions match. So I have 5x minus 1 times 5x minus 1. And again, I'm seeing if I square root 25x squared and I square root 1, 5x and 1 are my two numbers inside of the parentheses. The only difference is that we have a subtraction sign in between them. And finally, what we're going to do here is we're going to look at what happens when we have two perfect squares for a and c and no middle term. So here we need to start by identifying the values for a, b, and c. So I can see a is 4, c is a negative 25, and here I currently can't see b. And the reason we can't see what b is because there's no term with an x value. And what that really means is our b value is simply 0. If it's not appearing, our value for b is just 0. So here what we need to do next is we then need to use our multiply add trick from the ABC method. So I need two numbers that multiply to be negative 100 but add to 0. And as I start thinking through those factors of negative 100, what I remember is that 10 times negative 10 gives me 100, but these add together to be 0. So I can really rewrite this as 4x squared plus 10x minus 10x minus 25. And then I split it into pairs and look for the greatest common factor. So in this first one, it's 2x, so I have 2x times 2x plus 5. Then I want those parenthesis parts to match, so I'm going to factor out a negative 5 here. So I have plus negative 5 times 2x plus 5. And then from here, I can group together the 2x and the negative 5, so I end up with 2x minus 5 times 2x plus 5. So what I'm noticing here is that same square root trick where we square root 4x squared and we get 2x and we square root 25 and we get 5 still applies here, but what I'm noticing is that when there's a middle term where b equals 0, we have one parenthesis that contains a negative sign and one parenthesis that contains a positive sign. So from here we're going to apply the same thinking down below. Now because this b term is 0, and oftentimes it can get a little bit nasty with big numbers depending on how large your perfect squares are, what we're going to do is we're going to apply this pattern that we see. So what I've noticed is that I can square root a and square root c, and I end up with the numbers that go inside of my parentheses. So here I know that as I factor this 9x squared minus 100, I know that I'm going to get a set of parentheses times a set of parentheses. The only thing I have to figure out is what goes inside of those parentheses. Well, I know that if I square root 9x squared, I will find that first value. Well, the square root of 9x squared is 3x. So here I'm going to put 3x in the front of each parenthesis. I then square root 100, and I know the square root of 100 is 10. So I'm going to put 10 in the second part of my parenthesis. And then I need to look closely at this pattern here. What I notice is that I have 1 where it's a negative 5 and 1 where it's a positive 5. So in my final answer I have a negative and I have a positive. So the same thing is going to happen here. In one of these parentheses we have a subtraction, and in one of these parentheses we have a plus sign. So this would be your final answer. Now if you don't truly fully believe me, you can multiply this out, and what you'll find is that you get 9x squared minus 30x plus 30x minus 100. These cancel out, and you're left with just 9x squared minus 100. So if you're ever unsure if you did it correctly, remultiply it out and test it. So to quickly summarize what we've seen so far, if we have an a and a c value that are perfect squares, we can use the trick that we covered on the past 3 slides. So you know that as you factor these, they're going to end up with 2 parentheses times each other. So they're each going to end up the same way. And what you saw happen on each is that you can square root your a value, whatever that might be. So here in this case, the front half of your parenthesis is the square root of a with its variables, whatever that might be. And that was the same thing throughout. The first part of the parenthesis was always the square root of a with its variables. And then the second part of that parenthesis was always the square root of c with its variables if it has any. The only difference here that we found as we solved all of these was the signs that go inside of your parentheses. If you have a middle term that is positive or a middle term that is being added in between a and c, your 2 parentheses are going to contain 2 plus signs. If you have a middle term that is negative, your parentheses are going to simply have 2 subtraction symbols inside of them. And if you have a middle term that is equal to 0, you are going to have 1 of each. So that's really the only difference. If you see perfect squares for a and c, you can use this shortcut by square rooting each and putting them right into your parentheses, and then you just look at that middle term to determine do you have 2 positive symbols, 2 negative symbols, or 1 of each. So now let's mix these together in some equations. So what you're going to notice here is that we have a variety of polynomials. And the first thing we want to do with each of these is check our a and c values. So here we notice that we have a of 25m squared and c of 64. And what I'm noticing is that both of those are perfect square values. And as a result, I know that I can use one of my shortcuts. So I'm going to quickly write that, parenthesis times parenthesis, and set that equal to 0. And I know that to find the front part of each parenthesis, I take the square root of 25m squared, which the square root of 25 is 5, the square root of m squared is m. So the front of each parenthesis becomes 5m and 5m. I then square root the 64, which gives me 8. So the second part of my parenthesis is an 8 and an 8. Then I use this middle term piece, the fact that the middle term has a b value equal to 0, tells me that the signs that go inside of my parentheses are going to be 1 of each. And then from here, because this is equal to 0, we can utilize the zero product property because we have something times something equals 0. So we'll take each part and we'll set it equal to 0. 5m plus 8 is equal to 0, or 5m minus 8 is equal to 0. And then I start by solving each mini equation, and I find that one value for m is negative 8/5, and another value for m is equal to a positive 8/5. Okay, example 2, what I notice here is that I have perfect squares in 36w squared and 49. And what that tells me is I'm going to use one of my special strategies to help me factor that. So I square root the a value of 36w squared, which becomes 6w, and that goes in the first part of our parentheses. Then we square root the 49, and we get 7, so that goes in the second part of our parentheses. And then because this middle term is positive, we're going to put 2 positive signs inside of those parentheses. So then from here I can utilize the zero product property because I have something times something equals 0. So I set each part equal to 0. The first one I find w is equal to a negative 7/6. And then here I start by subtracting 7, divide by 6, and I find that w for this is also equal to a negative 7/6. So you can write this twice, or if you observe that they're the same exact value, you can also just write it once and say that w only has one singular value that will make that original equation true of negative 7/6.